In 2016, one oversized electrode inside a phone battery crushed a wall thinner than a hair. That crushed wall shorted a $900 flagship into an open flame. Break time equals 0, 6 is slash, and it grounded the Galaxy Note 7 from every airplane on Earth. August 2016. Samsung launches the Note 7 as its flagship. Reviews glow. Then the phones start burning. Samsung recalls them. Ships replacements. Those burn too. By October, the product is dead. Roughly 2.5 million phones pulled worldwide. Reported losses of roughly $5 billion. The FAA and airlines banned it, not just from carry-on but from checked bags too. So how did one phone become a flying hazard? The answer sits in a single crushed layer. Start with what a lithium-ion cell actually is. Picture 3 thin sheets stacked and rolled up tight. One sheet is the negative side, the anode. One is the positive side, the cathode. Between them sits a plastic film thinner than a human hair. That film is the separator, and it has one job. Keep the two metal sheets from touching. It must block the metal but still let tiny charged particles slip through. Those particles are ions, and their flow is what charges and drains your battery. So the separator is a gatekeeper. Ions pass. Metal stays apart. Here is why that wall matters so much. The anode and cathode are both packed with stored energy. The only thing holding that energy in check is that hair-thin film. Let the two sides touch, and all that energy finds a shortcut. Now think about what a short circuit really is. Current is supposed to travel a long, slow path out through the phone. A short lets it leap straight across instead. The current dumps its energy as raw heat, and it dumps it right where the two metal sheets meet. If the separator tears, the electrodes touch directly. If it gets crushed, same result. If something pierces it, same result again. Any breach and the cell shorts inside itself. That internal short is the trigger for what engineers call thermal runaway. Hold that phrase. But that raises the real question. What breached the wall inside the Note 7? So what breached it? Investigators traced the first recall to the original cells, later called Battery A. The problem was shape. Each cell lives inside a soft pouch, and inside that pouch the sheets are rolled and folded into a rounded rectangle. In the upper corners, the electrodes were simply too big for the pouch that held them. Think of folding a map that's slightly too large for its case. Something has to bunch up. Here the electrode bunched, and it pressed hard against the rounded corner of the cell. Right at that corner, the electrode pinched the separator. Remember, the separator is thinner than a hair, and it was being crushed against a curve with nowhere to go. Push a taut membrane against a sharp fold and it deforms. Push harder and it gives. That is exactly what happened at the corner. The oversized electrode squeezed the hair-thin separator until the gap between the two metal sheets nearly vanished. In some cells, it vanished completely. And the moment that gap closed, the anode and the cathode touched. That contact is an internal short circuit. No drop. No puncture from outside. No charger fault. The phone could be sitting on a nightstand, fully assembled, doing nothing. The defect was already sealed inside the cell at the factory, waiting. This is the part that unsettled people. You could do everything right and the battery could still fail because the flaw was built in. Samsung announced the first recall and swapped in a different battery. Problem solved, surely. But that touch inside the cell was only the spark. What turns a tiny short into a phone-melting fire? Here's where a spark becomes a fire. The instant the sheets touch, current floods the short and heat spikes at that exact spot. Heat is the separator's enemy. As it gets hotter, more of that plastic film melts and shrinks back. Melted film means more metal exposed. More exposed metal means a bigger short. A bigger short means even more heat. Heat feeds the short feeds the heat. That loop is thermal runaway, and once it starts, it feeds itself faster and faster. Temperatures climb into the hundreds of degrees Celsius in seconds. At that point, the liquid inside the cell starts to boil and turn to gas. That liquid is the electrolyte, the fluid the ions swim through, and it happens to be flammable. The cell swells, then vents that hot, flammable gas. Add the heat already raging inside, and it ignites. Now the honest question. Why should a battery this small do all that? A phone cell is tiny, but it is engineered to hold a lot of power in very little space, so you get a full day on one charge. Cram that much energy into a package the size of 2 stacked credit cards, and you have a genuine fire waiting for a trigger, not just a puff of smoke. The very thing that makes your phone last all day is the thing that makes a failed cell dangerous. Pack the energy tight enough and a pinhole short can empty it all at once. So battery A had a clear flaw and a clear fix. Samsung sent millions of replacements. Case closed. Except the replacements caught fire too. This is the twist nobody saw coming. The replacement phones ran a different cell, later called battery B, built by a different supplier. It should have been the safe one. It wasn't. And it failed for a completely different reason. Where battery A was crushed by an oversized electrode, battery B was undone by sloppy assembly. Investigators found sharp metal specks left over from welding, tiny burrs, sitting inside the cell where they didn't belong. They found insulation tape that was too thin in places. In some cells, tape that was supposed to protect a corner was missing entirely. Each of those flaws does the same fatal thing. It gives the anode and the cathode a way to touch. A stray metal burr can poke through the separator. A missing patch of tape leaves a bare edge exposed. Different defect, same ending. An internal short and the same runaway fire. Why so many mistakes at once? Timing. Samsung was racing to replace millions of phones after the first recall, and that pressure pushed the second battery out fast. Speed and precision pull against each other on a factory line. Here is the sentence that ended the product. 2 different batteries from 2 different suppliers, failing for 2 unrelated reasons in one phone. Fix one defect and you still have the other. There was no single part left to swap that would make the Note 7 safe. So Samsung didn't just recall it again. Samsung killed it. Full stop worldwide. But step back. What is the one lesson underneath both failures? Here is the whole mechanism in one line. The root cause wasn't fire. It was a fit. Both batteries told the same story at different scales. Battery A was designed with no room to spare. The cell was packed so tightly that the separator had no margin, no safety gap, nowhere to flex when an electrode ran a fraction too large. A millimeter of extra squeeze and the hair-thin wall gave way. Battery B proved the point from the other side. Even a clean design fails if the assembly leaves a burr or skips a strip of tape. Both come back to one idea. Respect the separator. Give that thin wall the space and protection it needs every single time. So Samsung rebuilt how it checks batteries. It rolled out what it named an 8-point battery safety check. X-ray scans that hunt for pinched or misaligned layers, charge and discharge stress tests, and design rules that leave deliberate breathing room around the separator. And the industry watched. One crushed membrane, invisible to the eye, forced the whole business of flagship batteries to prove their cells can't short from the inside. The failure that grounded a phone from the sky quietly rewrote the rules for every phone that came after. So there it is. One crushed separator thinner than a hair. 2 unrelated defects in one phone. And a total global recall that reportedly cost around $5 billion. A packaging error you'd need a microscope to see grounded a flagship from every airplane on Earth. If you want more failures like this taken apart layer by layer, the tiny defects that topple huge products, subscribe. Next up, why lithium batteries swell before they burn, and what that bulge is actually telling you.